Hi everyone, I hope you're doing well. Today we will cover dynamic programming from the very start to some like advanced problems. Let me share my whiteboard and let's start. So, uh, the most important prerequisite for dynamic programming is recursion. So, let's see an example using pure recursion. And let's and then see how dynamic programming can help us optimize our solution. So we are given uh, an infinite amount of one by one blocks, okay, like this, and two by one ones, like this, two by one. Our goal is to cover a ribbon of length n using these two types of blocks. The question is, how many ways are there to do this? Can anyone tell me how we can compute that? Yes, Haytham?
Do you want the complete search tool or the optimized dynamic programming?
Uh, Try to go for the naive approach.
We can use backtracking and recursion and keep putting any of the two blocks and see how many ways we can end up with.
Okay? So basically, um, we have a function. Okay? What would be the parameters?
The current index and the number of ways.
Index.
It's actually, I think, only the index.
I think you only need the index, yes. So here we have our function, type int. Okay? And so here we would try before to cover the case where we add a one by one block. Okay? So the result will get f of index plus 1. And we try the 2 by 1 block. And we add to the result f of index plus 2. Okay? For the base case, what would we have here? If the index is equal to n, then we return 1, right? And if the index is greater than n, we return 0, because we'd have a ribbon that's longer than n, right? Does this make sense? Okay. So here, let's try to compute this for n equals to 5. Okay. So it start at 0, the index 0. Okay. And here we compute f of 1 and f of 2. Okay. Now to compute f of 1, we will compute f of 2 and f of 3 To compute f of 2, we'd need f of 3 and f of 4. Here we'd need f of 5 and f of 6. Here, f of 4, f of 5. Wait, yeah, okay, that's it. Here as well, we'd have 3 and 4, 4 and 5. Okay, 5 and 6 are our base cases because n is equal to 5. Okay, so there is nothing anymore to compute here and here and here. Here we'd have 5 and 6. This is good. 5, 6, 5, 6, 4, 5, and here we'd have 5 and 6. Okay, so what we will do as each step, we will compute f of 3, f of 4, we will compute the sum of them, and this will be the result for this function. And we will have to do all of these operations to compute f of 0, right? You can notice that the computation we've done here is exactly the same as the one here, right? So there are things we are computing twice. Wait, I guess I covered the wrong thing. Yeah, that's it. Okay. You can see that a lot of blocks are repeating. Like, since we are computing, for example, f of 2 two times, all of the sub operations that heritate from it will be also done twice, right? You can also see here that f of 3 is computed 3 times, here, here, and here, etc. Right? So we can use simple trick in order to compute every element only once. Why? Because f of 2 is f is deterministic. So if we compute f of 2 now or later, it will give me the exact same result. Right? So we will use a technique named memoization. Memoization. Okay. Which will consist of, before calling our function, defining some vector. This can be integer or long, dp, okay, of length n here, and set it by default to -1. -1 means that we didn't compute yet f of I, okay? Like we have that dp I is equal to -1 means that we didn't compute it. Now, in our code, what we will do, f of index, okay? Now, if index is equal to n return 1, if the index is greater than n, we return 0. Now, if dpi is not equal to -1, we will return it directly. Okay, we return dp -1, dpi, sorry. Why? Because since it is not -1, it means that we have already computed it, and so we don't need to redo the operation. Okay? And now we just return dpi, which receives f of I plus 1 plus f of I plus 2. So basically, we are saving the result into dpi, and we are returning it. And so the next time the function will be called for the same index, we won't recompute anything. We will just return it from the array. Okay? Does this make sense? Okay, great. We can look back at here. So let's redo the operations in order. We want to compute f of 0. We will first compute f of 1, right? Which we need to compute first f of 2, which we need f of 3, which we need f of 4, which we need f of 5. This is computed. We're good. This is already computed. We're good. Now here, we've computed 4. Now to compute 3, we will need f of 5, which is already computed. Then we will need f of 2, which we'll need also f of 4, which already computed. Now when we go back to 1, we need f of 3, which will be already computed. And when we go to f of 0, it will need now f of 2, which we have already computed. So you can see here that our function have been called 2n times only. Okay? Well, it's 2n plus 1. But you can see that the algorithm here is O of n, which is much better than the naive approach, which has actually a time complexity of O of 5 to the power of n, with 5 being the golden ratio. Computing it is not our topic for today, but the important thing is that we had an algorithm that runs in exponential speed that have been optimized to using memoization to O of n, which is linear. Okay? Does this make sense? Any questions for now? Okay, great. So basically, we've seen here the first form of DP, dynamic programming, which is the top-down DP. Okay, this form is generally a function. Okay, that will use the result for the function for smaller subproblems. Okay, we compute f of subproblem 1, f of subproblem 2, f of subproblem k. Okay, and we combine the results, store them in the array dp, and return it. And whenever we call back the function, we return it from the array. Okay? This approach is called top-down DP. Now, let's see another example. Okay? So, to cadence algorithm. So, we are given an array of n elements. Okay? Say 1, minus 3, 4, 5, minus 2, 6, minus 24. Okay? We want to know what is the maximum sum of a subarray of this array. We define a subarray as some consecutive elements of the array. Like this one is a subarray, this one is another subarray, but like this is not a subarray since we are leaving some element in the middle. So the elements have to be consecutive. Who does have an approach for this? Yes, Faris?
We keep track of the sum, and if the sum goes below zero, then we don't take any element. Since taking no element gives zero, then we are in a better deal.
So basically, we go from left to right. Okay.
Yes,
We keep track of the sum. So
and
here
we
we
have
have
a
one.
variable max, like a max of the sum.
Yes. Okay. We have a max here. So here we keep track of the maximum sum, right?
Yes,
Okay. So here we have -2. Then here we have 2. So the maximum becomes 2 here. Okay.
no, but when we have -2, then we don't take any element because taking no element gives zero, which is better than 2.
Okay. So here we have 1. Here we have -2. So since we want negative, we stop here, right?
Yes,
And we start back. So here we will have 4. So the maximum becomes 4. We have 9. -2 becomes 7. 13. Here we have -7. So we stop. And here we have 4, right?
yes.
Okay. Can you tell me why this works?
Because like whenever not taking any of the previous elements is a better deal than taking them, then we don't take them. And when that happens is when we have the sum is negative.
Okay. So basically, what you're saying is that we want to know what's the biggest sum that ends in this element, right? AI. Okay. So if we have here that the biggest sum that ends here is negative, like less than 0, okay, it's better not to take it and start the value as the sum as AI, okay? But if it is positive, we just add the biggest sum that starts here, right?
Yes,
Okay. So basically, if dpi is equal to the maximum sum that ends at AI, okay, we have that this is equal to the maximum of AI, and I mean like taking AI alone, or AI plus dp I minus 1. Which okay, so let's start back where we started. So we have here that the answer for I, like the maximum sum that ends at AI, is basically the maximum between either taking AI alone, okay, or taking AI plus the maximum sum that ends at AI minus 1. And we can easily notice that this is bigger than this, if and only if dp I minus 1 is positive. Okay? And so the result for our problem will be, after computing all dp's, the maximum, okay, over dp0, dp1, until dpn minus 1. Okay?
I guess I can't see your screen.
Guys, can you see my screen, or the problem with Haytham is for everyone? Can't. Wait, it's me, sorry. Is it visible now? Okay, good. So, as I was saying, after computing the answer for every I from 0 to n minus 1, we just take the maximum over them. And this will be the final results to the problem. So here, instead of defining a recursive function, what we can do is that we define, after getting a from input, okay, and defining dp as an array of length n, we will set dp0 to a0, of course, and then for all I from 1 to n minus 1, dpi will receive the maximum between ai and ai plus dp minus 1. I minus 1, sorry. Okay? This is called a pool dp approach. Why? Because when we are here in AI, we are pulling the answer for previous results and using it for our computation. Okay? Another way of coding this, okay, is the push dp approach. What is it? So we still define dp0 as 0, as ai, sorry, a0, and then for all I from 0 to n minus 2, we set dp I plus 1 to the maximum between ai plus 1 and ai plus 1 plus dpi. So here, what we are doing is that when going through the array, we use the value and push it to the next one to compute it. Okay? So this is called a push dp approach. Like from the previous elements push to dpi, okay, to compute its final value. All right? Do you have any questions until now? Okay, good. Now, if we go to the first problem of the strip, okay? But here, instead of 1 by 1 and 2 by 1 blocks, we also have 3 by 1 blocks. Okay? How would we solve this? Anyone? Yes, Faris?
With the top-down DP or with the bottom-up?
However you want.
Okay. So, with the bottom-up approach, we can start from like have an array DP, which stores the number of ways we can fill the space till I,
Okay.
and we have that we can either place 1 by 1 block or 2 by 1 or 3 by 1. So we can have DP at index I is equal to the number of ways we can fit all the way to we can fit the blocks all the way to I-1 and add a block 1, or to I-2 and add a block 2, or to I-3 and add a block of 3.
Yes. And for the other approach, using pool DP, we can just use an array,
I
right?
Yes, and just change I+1 and I+2 and I+3 with the minus.
Yes. So we will try the uh, pool DP approach here, okay? So basically this is the number of ways to have a strip of length 0, okay? Which is always 1. A strip of length 1, which has also 1 way. A strip of length 2, there are 2 ways, like you can either have this or 2 blocks of 1. And the number for 3 is 4. Why? Because we can either have a block of 3 or a block of 2 and a block of 1, a block of 1 and then a block of 2, or 3 blocks of 1. Okay? And you can see that every value starting from here will use the 3 previous values, okay? And sum them, right? So here we'll have the sum of this and this and this, okay? So we will have here 7. Here we will have 13, and so on, okay? Now if you look at the graph, okay, such that the nodes are the elements of the array, okay, and there is an edge between going from dpi to dpj. If dpj is used in the computation of dpi, okay, like the edges we have here, okay. Can you tell me what's special about this graph? Yes, Haytham?
It is directed and acyclic, which makes
Exactly.
it a diag.
So for DP to work, we always need this graph to be directed and acyclic. Directed is obvious because of our definition here, okay? But the most important is it is acyclic, okay? But why so? Suppose that we are doing DP, and for computing DPI, we are using DPJ, which is using some DPK, and that same DPK needs DPI to compute, okay? So when trying to compute this, we will call the function to compute this, which will call to the function to compute this, which will call the function to compute this. But we didn't manage yet to compute the DPI. So we will keep looping. And so our algorithm wouldn't terminate. So the important thing about the graph of transitions, okay, like this we call it a transition in DP, like using DPJ to compute DPI, okay? So if the graph of transitions has any cycle, we will be unable to compute our answer. Okay? Does this make sense? Okay, so always remember that the transitions graph of dynamic programming is always and always a cyclic. Now, let's go to the next problem. For coin change. So, we are given a set of coins C1, C2, Cn, okay? Well, let's say Ck, okay? And we want to know how many ways there are to obtain a sum of x, okay? Using the coins we have here, each one in infinite amount. Okay? Like, for example, if I have the coins 1, 2, and 4, okay? And I want to have x is equal to 4. We can either use a coin of 4, 2 coins of 2, a coin of 2 and 2 coins of 1, or 4 coins of 1. Okay? So here we have 4 ways. Who can tell me how we can compute this? Does ways that have the same coins but different orderings count more than one way? Actually, no. Yes, Haytham?
We can define dp of I as the number of ways to obtain a total sum of I.
Okay.
So, and this time we need to care about the order in which we process the states. Like we loop from for each coin in our set, we loop from the last from n or x, the sum that we want to make, all the way down to 0. So that way we don't overcount any coin twice. Like we don't overcount different permutations of the same coins.
Okay.
Yes, and the answer will be dp of x.
Okay. So let me explain the approach. We'll make an array of length x. Okay.
Yes.
0, 1, 2, until x. And at the beginning, everything is equal to 0.
dp of 0 equals 1.
And dp of 0
Which is,
is equal to 1. Yes.
yes.
Now we will loop over the coins. Okay.
Yep.
And then loop for each coin c. Okay.
Yes.
What we will do is that for I going from 0 to x minus c,
No, in the reverse order. Wait. Can a coin be used twice or only once?
you can use it twice.
Ah, then from first to last.
So dpi plus c plus equal dpi, right? So here, if the coins are 1, 2, and 4, okay, and we're going up to 4, what will happen here? We start with 1, so we add one way to here, one way to here, one way to here, one way to here. So using the coins, the coin 1 only, we have one way in every one. Then we do the same for 2. So this will add 1 to here, so 2. This will add 1 to here, this will give 2. We add 1 to here, this will give 3. And we're done with this. And now for 4, we add 1 from here to here, it will give 4. And we are done. So we have one way here, one way, 2 ways, 2 ways, and 4 ways. Okay? Does this make sense? Okay. Now, why we are computing everything in this order is that like this, we are sure that all the ones have been added before all the twos, before all the fours, before every coin like this in the order. And so we are sure that we are not considering the case where we add a coin of value 1, then a coin of value 2, then a coin of value 1, right? Because every possible combination has a unique representation that is sorted like this. Okay? Any questions? Okay. Can anyone tell me what kind of DP this is? Yes, Faris?
Push DP.
Yes. Exactly. Because here we are pushing the result from I to I plus something. Okay? Like we push the value from the value we're computing the value from to the target value. Okay? Now, let's go for another example. Until now, we've seen only how DP can help us count things, right? But actually, we can also use it for optimization problems. Like if we are we can use the result after optimizing a small quantity to optimize a bigger one. So let's go for the next problems. Next problem. We still have a set of coins C1, C2 until CK. And we want to know what is the minimum number of coins to get sum x. Okay? Does anyone have an idea?
Can you say the statement again, please?
Sure. So you are given a set of coins, C1, C2 until CK, also in infinite amounts. And you want to know how many coins at least you need to use to obtain a sum of x. Yes, Faris?
We have a vector of DP as usual,
Yes.
and then we go over all the orderings as the first problem of coin change.
So what did you say?
No, like here we defined every value of DP as infinity.
Sorry, I didn't hear you well. Can you repeat?
We define every value of the vector DP as infinity.
Okay, sure. except of course
The 0.
the 0, which is 0, because we don't need any coin. Yes.
And then we go over all the orderings as in the first problem.
Yeah.
But this time we are going to use the minimum value of dp in at index I and dp at
Okay.
the previous value before we use the coin,
Okay. So
like dp
here,
at I minus c.
so here, if we have dpi, okay, we will use I minus c1, I minus c2 until I minus ck, right? And take the minimum value over this and add 1, right?
Yes.
So we either have a coin of value c1 or a coin of value of value c2 or a coin of value ck, okay? And we see which one allows us to minimize the sum, okay? Does this make sense?
Yes.
The others? So here the algorithm is very basic. So we have dp, which at the beginning is filled with zeros and infinities of length x. Then we loop over the elements for I from 1 to x. dpi receives the minimum over dpi minus c1, dpi minus c2, dpi minus ck plus 1. Okay, is this clear? Okay, right. Now let me give you a problem, okay? Uh, take 5 to 10 minutes to try on it on your own. Then we will do the solution together. Okay, guys. Did anyone find the solution? Yes, Haytham?
Uh, since the constraints allow for quadratic complexity, we can define dp of I as the maximum profit dp of I and 0 or 1 as the maximum profit we can gain on day I, and the 1 corresponds to buying on that day, and the 0 corresponds to selling on that day.
Okay.
Yeah, so when we're at some state, we can loop through all the previous states and pick the maximum answer between them. Like if we want to sell on day I, we loop on the days from 0 to I minus 1 and see which one gives the most optimal answer when buying on that day.
Okay.
And, and when we want to buy, we need to count for the cooldown that the task mentions. So instead of looping all the way up to I minus 1, we stop at I minus 2.
All right. This works, but a bit slow. Mm, yes, Faris.
What I thought is that we could have vector DP
Okay.
and we find DP as minimum as possible.
Okay.
All values in DP as minimum as possible, like negative infinity or something like that. And then we have DP at index 0 is equal to 0, since we can't buy or else we're gonna lose. Are you hearing me?
Okay.
And we can loop on through the values of DP, and we are going to make DP equal to DP at I minus 1 first. That's the first step. And then loop from all values from 0 to I minus 1. No, to I minus 2. Are you hearing me?
Okay. So this
And
is
then,
also
and
quadratic.
yes. And then we are going to say that if like DP at I is the max between its value and when we sell, when we buy and sell on the next day.
Okay.
Like when we buy on day I and when we buy on day J and sell on day I. I don't know if like the idea I explained is clear or
Yeah, I get it. It's similar to Haytham's one.
yes.
Yes, Haytham?
I forgot it raised from before, sorry.
Okay. Imran,
Okay. Can we use the greedy strategy?
what does it consist of? Like, what is your strategy here?
For example, if you you sell the stock the first day, then you keep track of you memorize the price of the stock at the first day, and as soon as the price become higher than first price, and the day is after the first sale day, you you sell the stock and buy one, etc.
Okay, like, uh, if I go from left to right, like I will buy, like let's say on Let's say that I buy on day one, okay, and I I go until it becomes cheaper, okay. Sorry, it becomes more, okay, like here, and I sell, right?
Yes.
Okay. So if we apply the greedy strategy here, we will buy on day one, okay. Then we will sell on day two. So we've made the profit of one. Then three, okay. I want buy here, okay. Then I buy on zero and sell on two, okay, because I can't buy on three. And so it will give me a profit of three, okay. Seems to work here. But now if I take this example instead, uh, like I will just edit the example a bit, 002, okay? Let's follow the greedy approach again. So here, we buy on one, we sell on two, okay? We skip this day, then we buy on zero, and we sell on two. So we make a total profit of three. Now, there is a better strategy, which is buying on one, selling, sorry, yes, buying on one and selling on three, then buying on zero and selling on two. You can see here that I obtain a profit of four, not three. Yes, Faris?
I solved the problem and I got accepted.
GG.
Yeah.
But we can do it in linear time.
Okay.
So who can tell me how to do so? Okay. I will tell you the solution. Wait. Yes, Haytham?
Uh, to make it linear time, I guess we can add a third state, like dp of I and k. K is between 0 and 2, where 0 corresponds to buying and 1 corresponds to selling, and the 2 corresponds to having a cooldown.
Okay, this works.
So a state can store the maximum among all the states before it, so no need to loop from first to last every time.
Yeah. We can actually do it in two states only. Let me
Okay.
show you. So, uh, we will define a 2D array, okay? So, here we will have the time t, okay? Which makes sense, which has to be in the DP array. And Imran, yes? I see you've raised your hand.
If we divide the array in two and do recursively the method then you show precedently, can't we make logarithmic time?
I don't see how we can make it logarithmic because we don't have an ordered array. So, no motivation for binary search or something like that, I guess. Okay, let's continue with the DP solve. So, here we have the time t, which is obvious. Like, we want to know what is the maximum after one transaction, two transactions, three transactions, okay? But now, well, no, not transactions, like after day. day 1, day 2, day 3 until day n. Now, what are the states here? It will be actually the last action done. Okay? So, if the last action was to sell, we put 0. And if the last action was buy, we put 1. Okay? So, let's say that we are here. Okay? Wait, let me just change the color. Let's say that we are here. Okay? The last action was sell. So, either we are selling on this day, like the last time I've sold something was on this day, or on the day before. If it was on the day before, so I can get the result from the previous day, okay? But if it is the current day, the last action was that was done before was buying, right? So it can be in the last day or day before. The most important is that the last action done was buying. So I will take here the minimum dp I 0 is equal to the maximum obtained, okay, on dp I minus 1 0 or dp I minus 1 1, like the last thing we've done was buy-in, okay, plus the values that I'm winning on this day, which is transaction on day 1, on day I, okay? Does this make sense for now? Like if the last action was selling, we've either last sold on the day before, or we are selling on this day, but we have bought before, okay? Now let's move to the next cell. The last action is to buy. So we've either bought on the day before, so here, or the last action was selling, but since we cannot sell then buy on 2 consecutive days, okay, we have to get it from here. And so dp I 1 is equal to the maximum between dp I minus 1 1 or dp I minus 2 0 minus ti. Why minus? Because we are buying, so we are losing money, okay? Does this make sense? Guys, any question?
Can you re-explain the state of the transition of dp of I and 1?
Sure. So, as I said, the last thing here that is done is buying, okay? So, the last time we bought was either on the previous day, okay? So, we are buying from here. So we get the state directly here. Otherwise, we are buying on this day, okay? And so the last time we have sold something was on the day before, because we cannot sell on day t and buy on day t plus 1. They already told us that this is forbidden. And so we will get the maximum sum obtained by selling here, okay? And we remove the value obtained by its transaction on this day, okay?
But maybe you sell at day I minus 3. No, it is
Yes.
possible.
The thing is that how did we define the state? It is
Ah,
not
yes.
the
Yeah.
transaction done on day I.
Yeah,
It
yeah.
is the last transaction done. Because it doesn't matter
Yes.
if I have sold on day I minus 2 or minus 3 or minus 4. The
I
most
see.
important is that the last transaction have been done before day I minus 1. Okay? Does this make sense?
Yes.
Any question, guys? Can you explain the transition? Sure. So, as I said, what the state means. We have dp, day, last transaction type. Okay? Like, it doesn't matter when we have done this. It only matters that we have done it. Okay? So, dp d0 means that the last thing we've done was buy-in. Okay? Sorry, selling. The last thing done was selling. It equals to the minimum between dp d minus 1 0. Like, we are not selling on this day, so we have sold before. So we're taking this directly from the previous state. Otherwise, we are selling on day d. So what does this mean? It means that we have bought something before. So the maximum from day minus 1 by buy-in plus selling on this day. So I don't know if it's x or t. Most important is that it's a transaction on day t. Okay. So we are buying, selling on this day. Okay, on day d. Now for dp d1, which means that the last action done was buy-in. Either we're doing nothing on today, so we're just getting the answer from d minus 1 0, or we are actually buying on this day. But the thing is that if we are buying this day, we cannot have sold the day before. So instead of d minus 1, we will do d minus 2. Okay, to implement the cooldown. So the last action done, sorry, this is a 1, was buy-in, either on d minus 2 or day before. So so we get the state from d minus 2, and we remove from it ti. Okay? Does this make sense? Any question? Okay, good. And for the base cases, just to make things easier, we will just define dp minus 1, like on day minus 1, 0, as 0. Okay? Same for dp minus 2. And for minus 1 and minus 2, but by buy-in, we will set it to minus infinity. Okay? Why minus infinity? Because it is impossible to buy something before day 0. Okay? And since we are maximizing things, the minus infinity will always lose. Okay? Does this make sense? Okay. Nice. So here you can see that adding more information about the state can help us solve the problem. Like, it's your solution to the problem does not have to rely on the given problem in the statement. But why 0 for buy-in? No, for selling. Selling is 0. Like the last thing was selling. It doesn't matter. But if by setting by into minus infinity is because we cannot buy anything before day zero. But selling with, like, it's like you've sold something with zero and that's all. Because initially you have 0 coins. Okay? So it means that we had no stock. Exactly. It's like we've bought something and sold something for the same price. The same. This just helps us like initialize our pocket to 0 coins. Make sense? Okay, good. Now let's go for a kind of classical problem, which is called the 0-1 knapsack. Okay. So you are given a knapsack, okay, that can carry a weight of at most big W, okay, and you have an elements that you can put in the knapsack, okay, that each have a weight of Wi and a value of Vi, and you want to know what is the maximum value you can carry in your knapsack. Like, you can see the knapsack as just some bag, okay, that can hold a weight of W, and you can get elements that have a weight of Wi and a value of Vi. And so you want to know what is the maximum value you can hold into your bag, okay? Who can tell me how we can approach this? Yes, Faris? Yes?
We can define a vector, a 2D vector dp. Now I'm going to start with the 2D memory solution.
Okay.
We are going to go over each item in like the order they gave us or any order, and
Okay.
we are going to define dp at the element at index I is the maximum uh, is is the maximum value that we can put inside our bag using all those elements.
Okay.
And we pass over the weights that from 0 to the capacity of the bag to maximize the value that we can hold.
Okay. Great. So we will define a DP array, okay, of size n times W, okay, such that, wait, let me move, DP ij is equal to the max value in a knapsack of size j using elements from 0 to I. Sorry, so this is 1 plus W, actually. Okay? And what is dpij equal to? It is equal to the maximum of either taking the element AI, okay? So maximum value I. So if we take it, the knapsack of elements from 0 to I minus 1 has size j minus wi, right? Because we are already carrying the weight of this, okay? Or we don't use actually this element, and so we just use dp I minus 1 with the same weight, j, okay? And if this is negative, we just set this to minus infinity to ignore it, okay? Does this make sense? So we basically either use the element I, and so we remove its weight from the possible knapsack weight, or we just don't include it and use the value from I minus 1, okay? Does this make sense? Okay, great. Now let's go to our last example. Let me just get the problem statement quickly. Okay. So we have NBs, okay? You know what's a bee? It's kind of insect, okay? The one that produces honey. Anyway, so the B1 is located on flower, okay? And has some information. So B1 possesses some kind of information. And wait, sorry. I have some instrument issue. Okay. Let me bring back the statement here. Okay. So as I said, we have at first a B, okay? The B is the B number one that possesses some information, okay? And each B has some friends, okay? This one has friends, this one has friends, this has friends, this has a friend, okay? So we have n minus one pairs of friends, and the B's talk only to friends. So basically we have the structure of a tree, okay? Each time, one B that possesses the information can pass the information to another B, okay? So here, this B possesses this information, and for example, for the next minute, this one can transfer it to this one, and this one can transfer it to this one, and so on, okay? And we want to know what's the minimum time needed for all the B's to know the information, okay? I will give you 5 to 10 minutes to think on the problem and know how much time at least we need for all the B's to all have the information, okay? Yes, Haytham?
I already solved this problem before.
Okay, so let's give 5 minutes to your friends, okay,
Okay.
to think on it, and then we can discuss the solution together.
Okay.
Okay, I think you had some time to like get at least a good idea about the problem. Haytham, can you explain your approach, please?
Okay. So we can notice that the given structure is the tree, is a rooted tree. The root is the node one. We can we can use DP approach here. We can define DP of I as the minimum time that BI can uh, can give information to all of its subtree.
Okay, good. So we define DPI as time,
Needed for BI to give information to its subtree.
okay, to inform subtree rooted at I. Good.
Yes.
And so our answer is DP1,
Yes.
of course. Great.
The base case is DP of any leaf equals 0.
Okay. Why? Because if it knows, if the root knows, we are already done. Okay, great.
Yes.
Then how to compute DPI if it's not
Yes.
select?
And DP of I, we will give priority to the child with that takes the most time to inform its subtree. So we will sort the children by the time that they take, like by their DP value.
Okay.
Sort them in the descending order.
Okay. So let's say
And
that. Let's try on this one. Okay.
yes,
So we have 0, 0, and 0. Good.
yes. So and for each of these children, now they are sorted. So the time that it will take to inform this child, let the index be I, one index. It will be DP of I plus I.
1, 2, 3.
Yeah.
So we take the
And
maximum sum.
the answer is just the maximum among these.
Yes. So here we obtain 3.
Yes.
Okay. Because, of course, it is better to tell a subtree that will take more time before a subtree that will take less time, of course. And since we have
Yes.
to wait 1 minute to tell the first subtree, we will have to wait 2 minutes to tell the second, and 3 to tell the third, and so on. So for this one, we have 0 and 0, 1, 2. So this takes 2 minutes to tell. Then here, we have 2 plus 1 and 0 plus 1, plus 2, sorry. So the maximum over them is 3 minutes. Here we have 3 plus 1, which is 4, then 2, then 3. So here the answer is 4. Here the answer is 1. Now over these children, we have 4 plus 1, 3 plus 2, and 1 plus 3. So we have 5, and 4. So the answer here is 5. Okay? Does this make sense for everyone? So basically we take the DP of the children, we order this value decreasingly, and then we add to the first element 1, the second element 2, the third element 3, until going to the last child. And then we take the maximum value over this. Okay? Does this make sense? Okay, great. So this is all for today's lecture. Do you have any question about what we've done so far? Okay. Thank you for your attention. I will try to share the whiteboard with you on the Discord and maybe some practice problem. And see you on the next session. But first, we should root the tree first, right? Yes, Haytham mentioned it at the beginning, I guess. Like you always root the tree as the first B, since it's the one knowing the information at first. Any other question?
Check the chats. Faris has commented.
Yes, I've just answered.
Okay, great.
Okay. Let's end the session here then. If you have any questions later, don't hesitate to tag me on Discord.